We're going to start with slide 90, but just by way of introducing slide 90, we have slide 86. Just to remind you that there were a couple of different categorical variable topics on the table today. And the one we've gotten to now is the categorical observed and continuous latent variables. Once again, there doesn't have to be a match between the variable type on the observed and the latent side. Any combination is possible, depending on the application and its fit to the data. And by the way, you probably recognize this combination as one that with maximum likelihood would call for numerical integration. So at some point during these 8 topics, we'll actually tell you what numerical integration is. But you know, you don't want to be too obvious, not yet. Anyway, so let's focus on slide 90. So there's a Swedish expression that a dear child has many names. Maybe it's US, actually. We're going to talk about item response theory, which is called latent trait modeling as well, which is called factor analysis with categorical outcomes. We're going to use the third term, but just to remind you that it's really then part of the topic of item response theory. So we're going to take a look at, first of all, a dichotomous dependent variable u. And we're going to have several of them, so we're going to put a subscript j, indicating that this is just one of the many dichotomous items. Say in an achievement test, multiple choice test given by ETS, for instance. So the y-axis varies between 0 and 1. And the x-axis in this case corresponds to the factor eta, or f, a continuous latent variable with a certain distribution. So we're going to do the regression of u on eta. And either probe it or load it would give you these kinds of S-shaped probability curves, indicating how quickly the probability of answering the item correctly increases as a function of an eta increase. And pictorially, you have the picture on the right. Categorical variables we write as u's, u1 through u5. Influenced by a single latent variable eta. And now we know that all of these arrows are straight arrows. They are actually representing these nonlinear relationships. Maybe you should have S-shaped arrows, I don't know. But they are indeed regressions, but they are probit or loaded regressions, 5 of them in this case. So we're looking at multivariate response. Item response theory then is a special case of a full structural equation model. So this builds on what we talked about yesterday all day long, where the response variable now can be written in a linear form as a function of the factor eta if you choose the underlying response variable formulation, u star, equals the usual intercept nu, the regression coefficient matrix, the lambda matrix, the loading matrix, plus a direct effect term from the x's, x influencing the response variables directly, and a residual epsilon. That's the measurement part of the model, and then the structural part, the factors possibly regressed onto each other via the beta coefficients and onto covariates via the gamma coefficients, and with our own residuals, the Greek z here. And then the connection between the u's and the u stars and the u's is through that threshold formulation that we looked at before. Certainly, that's just the same as talking about the loaded or a probit. Now, IRT typically only works with the terms that are not in parentheses. IRT typically works only with the terms that are not in parentheses. So you typically don't have the X here. You typically don't have regressions among the latent variables, nor do you have regressions of the latent variables on covariates. And even more typically, IRT considers a single latent variable, although there certainly are multi-dimensional developments of IRT. I'm pointing here to a reference on, I think, factor analysis of dichotomous items, which certainly has more than one eta. A couple of terms here. In the IRT world, the item parameter estimation is almost exclusively done by maximum likelihood, and in IRT literature, that's often called a calibration. I don't know why they have to have their own terms, but they do. Estimation of eta values is often called scoring, and they talk a lot about information functions. Assessment of information function is something that's very important to test development. And just to allude to that a little bit, it has to do with the linear factor analysis counterpart of factor determinacy. Factor determinacy, namely the quality of the factor score estimation for each individual. You know, for each individual can get a factor score estimate, but just like in any other estimation situation, the estimate can also be given a standard error. How uncertain is that person's estimate? And that was nicely reflected by factor determinacy in the continuous linear factor analysis case. But in this categorical nonlinear factor analysis case, it's a little bit more complex. As we will see, this information function has to do with the standard error, that is the precision with which we can estimate the individual's factor score, and it varies. It's not one and the same, but it varies, and it varies with the true value of the person's latent variable. So therefore, we're going to see these information functions having nice shapes. More about that later. Test equating is a common feature in the IRT world. Trying to, if you have an old test form and a new test form, trying to put the latent variable scores on the same metric so you can report them in the same scale. And that can be done in this Mplus framework as well by holding measurement parameters equal for items that are the same in the two forms. I think that's called anchor item equating. A lot of what we learn from IRT in the IRT area comes from educational testing, and a lot of it is very useful for transferring over into other non-testing situations, like mental health applications, for instance. And it hasn't been done fully, and particularly not with respect to longitudinal studies, where we can change items over time to better capture some construct. We'll talk about that a little bit in August when we come back and talk about multiple indicator growth modeling. Diff analysis in the IRT world is done in several ways. One is through these item response curves, where the curves that we have here on slide 90, I guess. And we let the computers sleep a little bit during lunch so they would not be slow in the afternoon. I don't know if you use the same trick. A diff would be curves that are shifted sideways for males and females, for instance. So there is a so-called item bias or differential item functioning. Can either be done within an IRT framework, or actually ETS, Educational Testing Service, uses more of a model-free approach. They use a Mantel-Hensel approach for diff analysis. In any case, some IRT terms. IRT models in Mplus, then, what is that? Well, we do now provide full information maximum likelihood estimation of IRT models with both logit and probit forms. we actually have had for a long time this capability in terms of weighted least squares, which is a limited information estimator using only bivariate information from pairs of items, and only available for the probit link. So now you have the full choice of estimators here. And we want to, let's see, slide 93. We want to make you be able to go back and forth in the easy way between IRT and IRT parameterizations and Mplus factor analytically oriented parameterizations. So we should then note a couple of things, that IRT calls the continuous latent variable theta. So they don't say eta. They say theta, we say eta. And, you know, their theta, that can confuse us because their theta is our residual variance parameter, right? So theta is their ability variable, and they're very interested in theta hat sub i's, individuals' ability scores for testing purposes. And the most favored model that they use is a so-called two-parameter logistic IRT model, and it looks like this. And it looks somewhat familiar, doesn't it? So e to the power of minus something is that argument is the logit, right? So the logit is d times a times the parenthesis of theta minus b. So they have then d set to 1.7, which is really close to square root of pi squared divided by 3. But not exactly, but close enough. So they have chosen that they don't, so let me put it this way. This is a logistic regression model with two parameters, like an intercept and a slope, except they change it a little bit. They use 1.7 so that the intercept and slope coefficients will be close to those of probit. If you make that 1.7, then the A's and B's for logit come out close to those of probit. So you go back and forth there, you won't be shocked at the almost 2 times difference. A is a discrimination parameter and B is a difficulty. A multiplies theta minus B. It doesn't multiply, it's not A times theta and then B, but you actually would have A times B here, right? So this is a parameterization that is chosen so that when the ability is equal to B, when theta equals B, that term then will be 0. And if that's 0, then e to the power of 0 is 1, so the probability is 1/2. That is, it's saying that when your ability is the same as the difficulty of the item, you have a 50% chance of getting the item right. So there is a reason for this madness of messing up the logistic regression formula. Okay, so that is the IRT parameterization. It's just a simple transformation of the parameters relative to what we have. And then you have the two-parameter normal curve. And again, we want to use a fancy word there. So we call it a normal ogive. Ogive, I guess, is a term for something that's curve-like. I don't know. You learn a lot of good Scrabble words from this. Although it may not be allowed. And in any case, in both on the left screen there, 93, you have the theta, the latent variable, assumed typically to be normally distributed. And you typically, just like exploratory factor analysis yesterday, you typically standardize it to mean 0 and variance 1. Now, so on the left is IRT, and on the right is Mplus. So Mplus, a factor analysis model parameterization, is much more directly related to standard logistic regression. The argument, the logit is minus tau for threshold plus lambda times eta. So with the trivial issue that minus tau is equal to the intercept. So this could say beta 0 plus beta 1 eta. So this is the logistic regression parameterization. And similarly for probit. In the probit case, we might bring in the residual variance here, theta to the minus 1/2 means that it's 1 divided by square root of theta. 1 divided by square root of theta can be written as minus 1/2. So theta is the residual variance. And if you go through this, you can make a conversion from the right screen Mplus to the left screen IRT parameterization. And this is described in a technical note that is on the Mplus website. There's a section on the Mplus website that is called Technical Appendices. And there's a lot of different items there. One of them has to do with IRT. And IRT actually has a special page. Either way, you come to a document which gives you the technical description of what we do in the IRT context, and you have then a conversion. So in Mplus, it's the lambda that plays the key role in when calculating A. The factor variance comes in as well. Psi is the factor variance, you know. But if that is fixed at 1, that term vanishes. And then you divide by that D, the 1.7. And it's the thresholds that then help determine B, the difficulty in the IRT world. So tau minus lambda alpha, etc., gives you the B. So if alpha is 0, alpha is the factor mean, right? In IRT we said on slide 93, bottom, alpha is 0, alpha being the mean of the latent variable, and psi is 1. So if you plug in 0 and 1 here, this term falls out. So B is simply tau divided by lambda. It's a very easy conversion. Probit conversion can also be made. And more importantly, conversions are automatically done in Mplus, at least for the standard cases. So you get not only the parameter estimates in IRT metric, but also you get the standard errors for those IRT parameter estimates. Testing the model against data, well, that's a tricky topic, actually, because when you have many categorical variables, the options for testing are a little bit limited. If you have a small number of items, say no more than 8 items, you could use the standard categorical data analysis approach of looking at the frequency table. So for instance, if you have 5 items, then you have 2 to the power of 5, namely 32 possible response patterns, right? If you write out the combinations of zeros and ones over those 5 items, there are 32 possible combinations. Those 32 possible combinations are the cells in the 5-way frequency continuity table. So 32 cells in that frequency table. The H1 model for that frequency table is a multinomial distribution, you know, the categorical variable counterpart to the unrestricted covariance matrix, mean vector, in normal continuous settings is the multinomial. So the multinomial H1 has 32 minus 1, since the probability is sum to 1, 32 minus 1, 31 parameters. And your model has far fewer. Your model has only some few taus and lambdas, 5 plus 5, like 10 of those. So you could test your model against the data or against the unrestricted model, same thing. And that's what you do in these familiar terms. The chi-square according to Pearson, chi-square subscript p, observed, which is the data, or alternative, you can think of that as the unrestricted H1 estimation, which will fit the data perfectly, and E standing for expected, which implies the model estimated. So O, you might write, O is the unrestricted H1 multinomial model. E is the H0 IRT model that you're interested in. And asymptotically, you have an equivalent test, the likelihood ratio chi-square, which does not, you know, the Pearson looks at distance between observed and estimated as the simple residual difference, but likelihood ratio takes a more sophisticated difference, just like ML looked at a more sophisticated discrepancy function between the data and the model than did ULS, that Linda talked about yesterday. So again, the maximum likelihood-based likelihood ratio distance is that O, the observed, times log of the observed divided by E should be small. Again, we want small chi-squares. If you have two large chi-squares, we reject the model. If you have large chi-squares, we reject the notion that our model generated the data. So we, throughout these two topics, yesterday and today, we want small chi-squares. And the problem with this is that when you get many variables, you get many cells. 10 variables is the familiar number 1024, right? To the power of 10, which you learn when you deal with computers. So 1024 cells with 10 variables, and therefore you get a great possibility of having many of those cells have low frequency. And we know from Stat 101 that when we have low frequency, we will get low model predicted frequencies, and that makes the chi-square approximation fall apart. You know, you're going to divide by something very small, you're going to blow up chi-square. So with large number of variables, which happens already with 9 variables, I think, these two are not going to be very closely chi-square distributed, and they're going to differ very much, which is a good sign that you shouldn't trust either one. So it doesn't help you, and the IRT literature tried to figure out other ways to check model fit. What we do in Mplus is to, when you can't look at the big frequency table for all variables, you can look at collapsed subparts, univariate and bivariate frequency tables, for instance, which you get the fit for in Mplus Tech10. And that also gives you the fit to all of the response patterns. And you may want to look at, say, the 10 most frequent response patterns and see how they give standardized residuals for these quantities to judge if the model is close to the data. But it's a little bit of a research topic. You see IRT being written about in the literature. The literature for IRT, I guess, would be Psychometrica and GEM, Journal of Educational Measurement, to a large extent, and to some extent, JEBS, Journal of Educational Behavioral Statistics. By the way, talking about journals, yesterday, for yesterday's content, you may want to start subscribing to the SEM journal, Structural Equation Modeling Journal. Has a good impact ratio, which is important, you know, when you apply for moving up in the professorial ladder, how often the articles get referenced, the impact factor. Psych methods is higher, though, which says that applications win, huh? All right, is this you or me?
Me, but could you go one more on that screen?
I'll be happy to.
Thank you. Okay, so now we're going to take a look at an example of IRT, and we're going to use the antisocial behavior data from the NLSY, Longitudinal Survey of Youth. And this is a really great data set. It's also complex survey data that we're ignoring, the fact that it is. We're going to be looking actually not at 15 of the 17 antisocial behavior items, but 8. We're going to look at the 8 property offense items. And these are dichotomous items, and they were dichotomized if 0 is never in the last year. And the factor was confirmed by doing an EFA first. All right, so let's just look on this screen at what the input would look like. So this is going to be a 2-parameter logistic IRT. So this is the IRT model using maximum likelihood. So down here we say analysis estimator equals MLR. That's a robust maximum likelihood estimator. We have our categorical option where we say that all the variables in the used variable list, the 8 property offense items, are categorical. And then in the model command, we're showing something a little bit different. Because IRT traditionally sets the metric of the factor by fixing the factor variance to 1, we're doing that. So we have F by property through goods asterisk, which frees up all of the factor loadings. The only one that was fixed was the first 1 to 1, but we can put the asterisk at the end of the list. So now all the factor loadings are free. And the metric of the factor is set by fixing the factor variance to 1. In the output command, you'll note that we're asking for Tech10. Those are the univariate and bivariate frequency tables that help us assess model fit when we have categorical outcomes. So we'll be taking a look at those. And we have our plot command. We're not going to look at that, but that's there. So the first part of the output is our test of model fit. And we don't get we get our log likelihood value and other information criteria. But what's of interest here are the 2 chi-square tests at the bottom. The Pearson chi-square, as Bengt mentioned. I guess we have to get the other screen to see the other one. The Pearson chi-square over there, and the likelihood ratio chi-square. And these are the 2 chi-square tests that fit the estimated frequencies versus the observed frequencies. And as Bengt mentioned, with more than 8 items, these aren't very useful because the frequency tables become so large. But in our situation, they should be useful, and they both agree that we should reject our model. So this would be telling us this model doesn't really fit the data very well. Other model results now that we show, here are our factor loadings, and because the items are categorical, these factor loadings are logistic regression coefficients. Remember, in a factor model, we regress the observed variable on the factor. So this is like an on statement, really, with property on F, but we use the by statement because we have to give the factor a name. So we name it F. So these are logistic regression coefficients. And we have the same output as always, but here's what you'll see in version 5. We have the standard error in the second column, the ratio in the third column, and then the p-value that's associated with that z-score in the last column. So that was something that came up high on the wish list, the Mplus wish list. Everybody wanted p-values, so now you have them. And then we have our thresholds. But more importantly, what we have on this screen is the translation Bengt talked about. So in a situation where you have a single factor model and you have categorical outcomes, we will, both with maximum likelihood and weighted least squares regression, we will do a translation using the translations that Bengt showed you. So here we have item discriminations, and on the next screen, item difficulties. And so these are using the translations that Bengt showed on page 90, or rather on 94. Let me just bring that back to show you. So down here in the left corner on the bottom is the logit conversion. So A is equal to what you see on the right, and B. So this is the conversion that we do automatically for you in Mplus if you have a single factor model and categorical outcomes. And then, so these are the discriminations, and on the next screen we find the difficulties. So that's the translation also. So there's really not too much to say about that. Bengt went over that pretty thoroughly. But now here we have our technical 10 output. So in the Tech10 output, we get several pieces of information. At the beginning here, we assign, it's sort of a lookup table. So we have the patterns of variables. So we have 8 variables. People could get them, they could have 0 for all 8 of the variables for pattern 1. pattern 2, they could have a 1 for the first variable, 0 for the second, 1 for the third, and 0 for the rest. So we would show all possible patterns. We're just showing you a subset here. And so and then we give you information about each pattern. So for example, on slide 105, and when you have categorical outcomes and you're using maximum likelihood where you don't get fit statistics, Tech10 can be very important and can give you a lot of information about where in your model the misfit may lie. So what do we have here? So we have response pattern, we have the numbers, and those are associated to the numbers on the left screen. Then we have frequencies. We have the observed frequency, which comes from the data, and the estimated frequencies, which come from the model. So you can see these don't agree perfectly. And down on number 5, you can see that the observed is 137, and the model estimated underestimates that by about 27. These other columns, we have the standardized residual, and then the chi-square contribution from the Pearson chi-square, and the chi-square contribution from the log likelihood chi-square. So what we're looking for here in the standardized column would be something greater than 1.96, for example. And we see pattern 5 has that. And then we also see large chi-square contributions for both chi-squares for pattern 5. So pattern 5 would be a pattern that we would be concerned about understanding why that pattern doesn't fit the data well. So if we go back over here, we can see that pattern 5 has 0 on the first item and 1 for the second and third items and 0 on the others. So now I have to remind myself what those items are. Okay, so those 2 items are shoplifting and stealing less than $50 worth of goods. Is that what that is? Stealing? Okay, less than 50. Okay, so yeah, so shoplifting and less than 30. So then what you might want to do, which we unpedagogically did not do here, and only realized it since we've been here, is you might want to go on to the next slide where we look at misfit, bivariate misfit. So we look at 2 variables, property and shoplift, property and shoplift, category 1 on property, category 1 on shoplift, category 1 on property, category 2 on shoplift, 2 property, 1 shoplift, 2 property, 2 shoplift. So that's how you read these numbers. So they're the cells of the table, and we then look at the standardized residual to see which cell might have a problem. And once again, you're looking for something that's large. Now here we don't see any problems here. They're all less than 1.96, for example, if you choose that as your critical value. Now on this slide, you should cross out property shoplift. I think this battery might be getting a little weak, Bengt. Oh, okay. Yeah. So if you just cross property shoplift off, that's a mistake. So the variables that are being looked at here are less than 50 and greater than 50. And once again, we have our cells, and we go over here, and we look at the standardized residual, which is a z-score. And we can see we have one cell that's problematic. So that's category 1 on less than 50 and category 1, or 2 rather, on greater than 50. And we can see the estimated probabilities for those. So there's 4 cells. Our H0 is the model estimated. H1 is the observed. So this represents the 4 cells observed. This represents the 4 cells estimated. And we can see that for this, the model overestimated the value. So, basically, this is how you would use this information. And you might add a residual covariance, for example, between those two variables to try to get that to fit better. And even though we don't estimate variances for categorical variables, one can add a covariance between them. But it's easier to do this in weighted least squares estimation than in maximum likelihood, because each residual covariance you add in maximum likelihood, and you can't add them using the with statement, you have to do it in a different way, which is illustrated in the user's guide. But for each one you add, it's one dimension of integration. And we haven't totally gotten into this topic, but when you have numerical integration, more than 4 dimensions of numerical integration is pretty much computationally hopeless. It's the word that comes to mind. But anyway, it just becomes, with a model that has more than that, the results may not even be meaningful at that point. So you would, if you really needed to add a lot of residual covariances, you should go to weighted least squares. But in maximum likelihood, it would be a dimension of integration for each one. But this type of information, when you look at your model misfit, it can suggest, parameters that you might want to add to your model. And that's Tech10. And now we have some plots that I'm going to let Bengt talk about. And these come through the plot command. So actually, I said we weren't going to see them, but we are going to see them.
So now you may ask, first of all, do I have to translate my results to IRT metric when I do categorical factor analysis? No, you don't, of course. It's only if you want to talk to IRT folks for whom a difficulty of 1.5 means something. The value is really in a metric that they understand. So no, you don't. It's just if you communicate in IRT terms that you might want to do that. So item characteristic curves, ICCs as the IRT people call them, and which should not be confused with the intra-class correlations. They are simply the probability curves, on the y-axis, the probability from 0 to 1, on the x-axis, the predictor of the probability, in this case, the factor. That's all it is. Item characteristic curves. You can get them for each item in Mplus or for all of the items. So your task is to look at them and make them tell you something. So it looks like the item with this color. Which color is that? Well, you can designate that color yourself. For that item, it's an item that has a curve that goes up fairly far to the right. And then you know that that's a difficult item, right? It takes a high factor ability for a probability to be significantly high, substantially high, I should say. And most of the items seem to have fairly parallel curves, which would indicate that they have fairly similar loadings. And I think that's true in the IRT framework here. The loadings hover around 1, 1.5, and there's only conning that seems to have a lower 0.7 discrimination, which discrimination being the loading. So maybe conning is this, to me, purposely looking a line which has a somewhat flatter slope, this one here. Yeah, it looks like that could be con. It's hard for a color challenged person to tell. But in any case, so the steepness of the curves correspond to the item discrimination values, and the location of the curve sideways has to do with the difficulty. So the higher the difficulty value, the highest difficulty value seems to be for auto. I guess that's stealing a car. That's probably this curve out here, the auto curve, saying that that's the most difficult item. But you have, of course, have to translate now from from IRT language, it has to do with abilities, to misbehavior item, you would say it's the most extreme item. It's the most extreme item. It takes a lot of antisocial behavior factor, very high antisocial behavior factor value for you to admit or commit an auto theft. So that's basically how you read that, and the variance was standardized to 1 in IRT fashion, and by default the factor mean is standardized to 0. So the factor mean 0 sits down there on slide 108, and it looks like you have to be above the mean of the factor for the probabilities to have any substantive, be of any substantial degree, amount. You have to be higher on the factor than the mean for you to engage in the bad behavior, saying that most people in the population don't engage in that with very high probability. Here's the test information curve then, using IRT language. It tells you again, it's the inverse of the standard error for the factor scores. You know, standard error, when standard error is small, the information is high. When standard error is small, the precision is high, right? And information is the same as precision. So it's really the standard error or the variance inverted that the test information shows. So this is from maximum likelihood theory that you derive this, where you estimate something, and through the estimated so-called information matrix, you get the standard errors or the variances of the parameter estimates. And here you can plot it. You can plot it as a function of the true factor value, saying that the information is high here, that is, the precision is high with which you estimate an individual's factor value, if the true factor value is up here, 1.5. But it's much lower if a person is on the low end of antisocial behavior or on the very high end. In any case, the peak is not at the mean, which implies that you can estimate factor scores for individuals who engage in this problematic behavior well, but you don't estimate factor scores that well for individuals who are at the average. So these items that you see on the left are geared towards measuring people who engage in bad behavior. If you wanted to measure people's behavior a little bit better, you should have some items that are less extreme sitting out here with lower difficulty, so to speak. So, you know, like coming up with a white lie now and then. Something like that. So you get the idea. So educational researchers are very interested in getting a high and broad peak. So they choose the right test items to measure well over a wide range of factor values. So that's what keeps ETS going. Now, you can also, all of these plots are from Mplus, and you can also get a histogram for the estimated factor scores. Estimated factor scores are, it connects with statistics estimation of random effects for individuals. In this case, random effects are the continuous latent variables of the factors. And the standard statistical method is what's called Empirical Base. That's looking at the posterior distribution of the latent variable given the data and the model. Usually we go with the other way around when we model things. We talk about the distribution for the data given the model, but here we're talking about the distribution for the factor, the unobserved, given the data and the model. So we have the way it goes is that you have a prior for the factor distribution, and typically being normal, and then you get the data, and you do a maximum likelihood estimation, and then you can derive the posterior distribution. So each person's response pattern under the model gives a posterior distribution for that person's factor value. It actually has a peak somewhere, and you pick the expected value of that posterior distribution as the best estimate. But really, each person has can be given a curve of values And you're just picking the mean here. Another approach is to pick the maximum, but we pick the mean in line with standard IRT. Now, the posterior can look quite skewed, as you have it here. Even though the prior was normal, the posterior looks quite skewed. It doesn't necessarily mean that your assumption was wrong. It means for the normality, it just means that you didn't have a lot of items that discriminated with lower difficulties. If you had more items with low difficulties, these people at the lowest factor score value would be spread out into a tail, which may well look normal. So that's more of a niche feature of item choice, item wording. Anyway, just showing you some plots. Further readings on IRT. I used to teach a course on that, a 10-week course at UCLA using this old book, Hamilton and Swaminathan. Swami being at Amherst, Massachusetts. That's a good classic one. Now Baker and Kim has a more recent one, 2004, quite technically oriented. Darabach gave a nice talkative history item response theory. Darabach also has developed a lot of IRT programs in his scientific software company in Chicago. Bilog, multilog, parscale, test fact. And essentially we do bilog, multilog, and test fact in Mplus. Here's a very applied book, Item Response Theory for Psychologists by Susan Emberson and Steve Rees at UCLA. And here's my dabbling in IRT related to instructional sensitivity. That is, you have information on whether or not an individual solves an item correctly, but you also have information about OTL, opportunity to learn, how much they have studied the topic, item-specific information on that. So trying to tie those two pieces of information together. And Yoshio Takane and Jan DeLeo wrote in Psychometric on the relationship between item response theory and factor analysis of discretized variables, basically coming to the conclusion that they're one and the same. All right. So now, Linda showed you an IRT example which pointed to the fact that the model didn't fit as well as it should have. And perhaps one reason, it could be several reasons for that. She brought up the possibility of residual correlations between items that were unaccounted for. That's really a first step towards thinking maybe there is a second factor. You know, if you have a second factor influencing the items, then certain items would correlate more than what's explained by one factor. You can go from residual correlations to minor factors to major factors in your thinking. And really the first step should be exploratory factor analysis. And IRT people have done that in the past. There are techniques for that. E.G. Muraki in Chicago UIC has worked with Darabach and others to develop the so-called test fact program. How many of you know test fact? All right. So Mplus now does test fact, which is exploratory factor analysis for using maximum likelihood. Before it only had limited information weighted least squares estimation. So Mplus then, as is explained in the user's guide in chapter 4, does exploratory factor analysis for all these kinds of outcomes: categorical, censored, and counts. And by categorical, we mean binary or ordered polynomous. The unordered case is not included here. And you can have any combinations of such variables in your data. So I should have mentioned that one of the combinations can be continuous. So a typical combination, common combination, I would say, is categorical items together with continuous ones. And you can do that exploratory factor analysis with rotation of the factor loading matrix, just as with continuous outcomes, using either maximum likelihood estimation or limited information with least squares estimation. If you have time before you head off at the very, very end, I may say a few words about limited information weighted least squares estimation. But maximum likelihood, it is a useful technique. It is, a very good estimator, efficient in the sense of providing small standard errors. But it's computationally feasible for only a few factors due to this requirement that you have to use numerical integration to carry out the computations. So a few factors, but can handle many items. It's not so restricted by the number of items. Frequency table testing is typically not useful, so you will have to rely on Tech10 or other means. Limited information weighted least squares estimation is computationally feasible for many factors, but not a huge number of items. I think maybe 100, something of that order. So you sort of can combine maximum likelihood and limited information. What we don't have is a good technique for many items and many factors. That's tough. Here you'd get a chi-square, overall chi-square test for the weighted least squares. That is very similar to what you get in SEM, which might be one advantage for using this approach. And it's very easy to allow for residual correlations, much easier than with maximum likelihood. Now, let's take a look at the assumptions behind this model a little bit, because it also sheds light on a classic debate about, here's another cocktail word, tetrachoric correlations. Not tetrachloric, choric. All right, so if you look at the latent response formulation of a factor model, of the IRT model, we can write it by introducing this layer of latent response variable U stars. We don't have to. We can say that F directly influences U through a logistic or probability regression, but we can conceptualize it as an equivalent model, saying that this is a linear regression here, and then when U1 exceeds the threshold, tau 1, we get U1, the observed U1 equals 1. So this is equivalent to loaded probability regression, but it really shows that some key issues, which we have on slide 115. So note that when assuming normal factors, normal F in this case, and using a probit link, what does that mean in this picture, using a probit link? Well, you have to look at the details. Here sits the little delta, or was it epsilon? The residual in the U star equation, in the linear regression. If that is normal, we agree that that was the same as probit regression, right? We had the picture and the formulas. So if this is normal as opposed to logistic, then this is a probit link. So if this is normal, and that is normal, then what can you say about the distribution for the U stars? In statistics, you have the answer. The variable that's normal added, and if you add another variable that's normal, the sum of two normals is normal. So the U star variables will be normal. The U star variables will be normal if you have a normal factor and normal residuals, namely a probit link. Then you can talk about U stars that are multivariate normal. This is what the weighted least squares model works with, that assumption. Multivariate normal U stars. And then what the weighted least squares approach then works with are the correlations between the U stars. Latent correlations. It fits the model to the estimated latent correlations. And those latent correlations between the U stars are called tetrachoric correlations. Tetrachoric correlations for dichotomous items, polychoric for polytomous items, polyserial correlations for combinations of continuous and categorical items. So some people criticize tetrachoric correlations for two reasons. They don't believe in underlying variables, and that's nonsense, as we've said, because it's the same thing as probit loaded regression. And then they criticize them for assuming that the underlying variables are normal. Well, that's what IRT does all the time, because it assumes that this is normal. And if you just add a probit link, you get normality. If you add normal plus Logit error, you don't get exactly multivariate normal, but close enough. So there's really no difference. It's just the way it has been poorly portrayed in the past that has raised the critique of tetrachoric, polychoric, polyserial correlations. The advantage of ML is that it uses a continuous table. If you have 5 items, it uses all 32 response patterns, whereas weighted least squares uses only pairwise tables, pairwise information from each pair of items. So that is a good segue then into slide 117, which leads to an interesting set where you have this picture 117 shows you that, say that you have these underlying response variables. If you could measure them, you could see that they are, well, let me put it this way, and you specify them to be bivariate normal with a certain correlation here, the bivariate normal, but what you measure are the U's for 2 variables here. UI and UJ are 2 variables. And just by question wording, you know, from, if you look at this item here, strongly disagree to strongly agree, a Likert scale 1, 2, 3, 4, 5 categories, that UJ looks very skewed. That just happens because the thresholds are chosen, the item wording is chosen so that you don't distinguish between the people at the high U star J range, but only at the low. So even though the items are skewed, the original U star variables can still be bivariate normal. And it's, so the way you estimate these latent correlations between the U stars, in this case polychoric correlations, would be to use the bivariate table for one variable with the other and derive the correlation here and the thresholds on the underlying U stars. So that is what weighted least squares does, working with these latent variable correlations. And here you have a summary, types of U star correlations, both dichotomous, tetrachoric, etc. Biserial being a version of polyserial. You may want to add 2 more terms here, just in your collection of terms. How about a phi coefficient? What's a phi coefficient? PHI coefficient. Phi coefficient is a standard correlation coefficient. What's a standard correlation coefficient called? You know, the one between continuous items? Pearson correlation, right? A Pearson correlation for 2 binary items, for 2 dichotomous items, is called a phi coefficient. So that's the observed counterpart to the tetrachoric. And then the observed counterpart of the biserial is called a point biserial. Point biserial, when you use a Pearson correlation for 1 dichotomous, 1 continuous. And I bet you there's also point polyserial out there. I won't talk about the bottom of slide 118. But anyway, so you have a collection of psychometric terms. We have to carry that oral tradition forward. Is this you or I? Me. Okay, so let's take an example then on slide 119. And now we're going to analyze 17 ASB items using a weighted least squares approach. We say that we work with all of those 17 in the use variable list and declare all of those 17 items as categorical, in this case dichotomous. We request an exploratory factor analysis and extract 1 through 5 factors, just like we did in the continuous case. So the only difference is really the categorical equals line, but a lot of difference behind the scenes in what the program does. And we can ask for modification indices, which pertains to the residual correlations, the off-diagonal theta elements, as we say, and we ask for plots. Here's the plot. Here's the eigenvalue plot from Mplus for the tetrachoric correlations among the 17 ASB items. And I got the weighted least squares estimator by not requesting maximum likelihood. So the default here for EFA is weighted least squares. If you want maximum likelihood, you would have to say estimator equals ML here on slide 119. But you may not want to do that because you go up to 5 factors, and 5 factors is 5 dimensions of integration. And what was Linda's technical term for that? Huh? It falls apart, I think she said. Doesn't sound good. So anyway, you have the eigenvalue plot here, which you can, on the y-axis you have the eigenvalue size, and on the x-axis the number of factors that you extract. And once again, you can look for an elbow, how many factors exceed a line created from these. And maybe it's 1, 2, 3, 4, I'm not sure. It's hard to tell. Most cases it's hard to tell. This is just a descriptive. Just a descriptive help. What are the statistics for this? Well, here you have a model with, since you're working with weighted least squares, you get model fit indices that are similar to the continuous case that we discussed yesterday. You get 88 degrees of freedom and 584, which, you know, chi-square is much too high relative to these degrees of freedom. You know that the expectation of a chi-square variate with 88 degrees of freedom is equal to 88. The mean of chi-square is equal to its degrees of freedom. So this is much too high, which says that p-value is low, which says that your model is most likely not generating these data. But you do have a large sample here. And not only that, you have a complex sample, which we ignore in this case, so you may overestimate the chi-square. If you look at the common fit indices like comparative fit index, Bentler's fit index for an SEM, it's certainly greater than 0.95, 0.96. It's very high and would suggest that maybe you have a reasonable fit. Root mean square error of approximation and SRMR are also good indicators of fit. This is for the 3-factor model, I believe. Here you see the quarti-mean rotated loadings. So this is using version 5.0. And you have the substantively important loadings here using Linda's rule of at least 2 times. I haven't marked the significant loadings here, but property shoplift less than 50, greater than 50 is one dimension. It's property offense, perhaps. Second dimension, fight, threat, injure, that's personal offense. Third dimension is pot, drugs, sold pots having to do with drugs. And let's see, here are the quarti-mean factor correlations. I think we have the 4-factor solution here. Chi-square drops quite a lot, becomes better. And the 4-factor solution on slide 127 suggests that we have a clean factor structure here. Factor 1 on slide 127 is property offense, shoplift, less than 50, greater than 50 stealing. And I'll do this. It continues on slide 128, and the property offense continues into auto, building, and goods. So how many items are those? 1, 2, 3, 4, 5, 6, 7. So it does suggest that there are 7 items here. I can't remember which item extra that I brought in. I think it was con, actually, down there. I think we had con. We had 8 items when we did IRT. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I think I brought in con. And if you look at slide 127, con is a little questionable. It sort of loads on the second factor almost, well, to a large degree, 0.2. And the second factor really is a person offense factor, fighting, threatening, and injuring, not so much a property offense factor. And are there other items among those 8 that load on that second factor and would explain a correlation? Let's see. Well, gambling certainly are, but that's not included in the set. But some of these items, property has a loading 0.19, almost 0.2. And yeah, you have a little bit of noise there. But essentially, I think we picked out the right items. Maybe you want to delete con based on the factor analysis and work with 7 items for property offense, and maybe that would fit better. In any case, this is the quarter-mean oblique rotation, so you get the factor correlations here. So this is EFA for categorical items using the weighted least squares estimator. Quite handy and fast. Certainly 17 items is no problem at all. And what was it? 7,000 observations, no problem. And you could do this with taking the complex sample features into account. Using type equals complex and MLR, no problem. And by that, I think practical issues sounds like.
Okay.
Sounds like
But now with your fourth factor, you would choose the 3-factor solution, right? Because the fourth factor only has one.
Okay, that's a good question. Would I choose 3 or 4 factors? Can we have a consensus on that? Would you choose 4 factors? Good point. The fourth factor has no good loadings for these items on the right screen, and only 1 substantial loading for the first screen. So yeah, three factors would seem, the fit indices are not always precise, but if you look at the loading matrices for adjacent number of factors, you certainly would choose 3 in this case.
Okay. So just to also...
Hold that question until later, if you don't mind.
We'll take questions at the end. So just to remind you that when you do exploratory factor analysis, the ultimate deciding factor is, do the factors make sense according to your theory? So, you don't let statistics helps you decide. It doesn't make the decision for you. So let's talk about practical issues in the analysis of categorical outcomes. So the question is, when is a variable best treated as categorical? And it's really less dependent on the number of categories than the presence of floor and ceiling effects. So if a variable has 7 categories, but it has a strong piling up either at the highest category or the lowest category, you should treat it as a categorical variable. And likewise, with less categories, 5, if you don't have a strong piling up at either the highest category or the lowest category, you could consider treating it as continuous. And we're going to take a look at what happens when you do this. And then what is wrong? If you do treat categorical variables as continuous, what happens? Okay, your sample correlations are going to be attenuated, particularly when you have floor and ceiling effects. And you can end up finding factors that aren't really substantively meaningful, but just have to do with the extremeness of the items. And you'll get predicted probabilities in this situation that go outside of the 0-1 range of admissible values for probabilities. Is this the good one? Okay, so let me get both of these pictures up at the same time. All right, so on the right screen, here's an example of a categorical variable with 5 categories where there is not a piling up at either the lower category or the upper category. And it may lead to incorrect standard errors in chi-square under normality assumptions, but you could transform a variable and treat it as a continuous variable and use non-normality robust maximum likelihood estimation. So you could treat this variable as a continuous variable and use a non-normality robust estimation for that. And as we're going to see, you're probably not going to be far off with 5 or greater categories. And if you're not interested in talking about probabilities, then you might want to do that. But if you're interested in discussing your results in terms of probabilities, then you would have to estimate the model with categorical methodology. Okay, and we have the same problem here. We're going to have incorrect standard errors, chi-square, and parameter estimates under normality. But in addition, we have a situation where we have piling up at the lowest category. And no transformation, no non-normality robust estimator can help you in this situation. So if you have categorical variables that have any number of categories, and you have a piling up at the end, you know, whether it be a dichotomous variable that has a really 90-10 split or something like that, or a 3-category variable where there's piling up here, or even, you know, a 9-category variable that has piling up at either end. Non-normality robust estimators can't help you. You really need to use categorical variable methodology to estimate your model correctly and get correct results. Now here's the picture that Bengt just showed you, and what happens when you have certain situations, you're not able to capture this correlation between the two U stars. It becomes attenuated and you don't you're not able to estimate the U star correlation correctly when you have strong piling up. And we're going to look at different situations and see how much we go wrong. So you can create a situation where you have, for example, okay, so the phi coefficient that Bengt mentioned to you is a Pearson correlation on binary items, for example. So that's simply if you use SPSS or something and you do a Pearson correlation and your data is binary, it's actually going to come out to be a phi coefficient. And they're unsuited to categorical variables most of the times because they're limited in the range they can take on. They can't, in some situations, they can't get larger than a certain value. So for example, if you have, if you look at the table below, if you have a situation where your marginals are 50 and 20, so we have a table with 4 cells, the 0, 0 cell has 50, the 0, 1 cell has 30, the 1, 0 cell has 0, the 1, 1 cell has 20. With these marginals, no matter how the marginals come about from inside of the 4-way cells, you know, if it's 40 and 40 or whatever ends up, and then that's 10. But however you get the marginals of 50 and 20, you're never going to get a maximum Pearson correlation greater than 0.5. So you have a limitation there. And so that restricts you from seeing the true correlation between the U star variables. And this next screen just shows you how to compute the formula for the phi coefficient or the Pearson correlation and shows the maximum value is 0.5. So now let's take a look at a situation on the left screen where the correlation between 2 U stars is 0.5. So that's sort of the population value. The true value is 0.5. What happens in this situation if we have 2 dichotomous variables that have 50-50 splits? So we have 2 cells and they both have 0.5 in them. So it's a rectangular 50-50 split. If we get a phi coefficient for those, it's only going to be 0.33. So we have the correlation should be 0.5, but it's attenuated, and the value we get is actually 0.33. If we decide to split the 2 variables 1090, so we have 2 categorical variables that are split 1090, then we're going to get a phi coefficient of 0.25. So that's really only half the size that it should be. And we can look at 3 categories down here. We have sort of a normal type looking split, 27, 46, 27. We have 2 variables like that. We're going to get 0.41. If we have a rectangular distribution, 33, 33, 33, we're going to also get 0.41. And then if we have some piling up at the end, so that it's 14, 29, 57, we're going to get 0.39. So you can see that we will get attenuation in these situations. And so we will be not really fully taking advantage of the strength of the relationships in our data. Some more examples of this. As we move up in the categories, you'll see that things get a little bit better. So for example, if you have either the normal looking or the rectangular split with 16, 34, 34, 16, or all 25, we get 0.44 instead of 0.5. Once again, we see that this ceiling effect here, the piling up at the highest category, we get a smaller correlation, 0.41. And with 5 categories, we do quite well with both the rectangular and the normal-looking distribution. These get 0.46, and with the piling up, once again, it's attenuated a little bit more. So we actually did this little study and created this summary of information. We also have a table that you can look at to see what happens, which just takes us a little bit further. So here we have 2 parts of the table. Bengt always likes it when I go from left to right instead of right to left. So how do we read this table? Let's take a look at it. So basically, we have the columns represent D, dichotomized 1090, dichotomized 2080, dichotomized 3070, etc. And we have the same thing down here. And then we come to a category which is 3 symmetric, 3 rectangular, and I don't know what NS and PS. Oh, 3 negative skew, 3 positive skew, etc. So from dichotomous to 3 categories to 4 to 5, and the exact same entries along here. And what we find, and the true value is 0.5. So there's a lot of values in there that are not 0.5. So let's take a look at the worst case. The worst case is if you have opposite skew, 90-10, 10-90. And instead of 0.5, you get 0.1. So, that's a fairly serious situation. And then what is the best situation? What's the highest one? Let's see. Well, and one thing I didn't point out, we have at the bottom treating them as continuous in both cases. We actually get 0.5. And I think the highest one I see is 0.46. 0.47. Ah, there it is, right here. Okay. So the highest one is 5 symmetric, 5 symmetric. So when you have Likert scale variables that are symmetric, then you can possibly, if you have a reason to do so, treat them as continuous variables, and you're not going to be that far off. So this table, gives you a summary and gives you a good idea of where the problems are. Extreme skews in the opposite direction are the worst situation, and 5 category symmetric is the best situation. Even better than 5 category rectangular, although that's pretty close. So this is just a little table that we created that we thought you might find interesting to show you in which situations you really ought to consider treating the variables as categorical rather than continuous. Now, what other approaches can you use to categorical outcomes? Well, basically, you can either look at items on the item level, test sets, which are sums of items, sum scores, or factor scores. So there are options there. Let's say that you have at least 15 items, and like we talked about this morning, you have 15 or more items, and you know that they measure the same factor. So knowing that they measure the same factor is the important part here. Then you can just sum them up, and you can use the observed variable in your analysis. then you don't really need to worry about dealing with categorical variable methodology, because you would treat that sum as a continuous variable. And if you're in a situation where you have a lot of items, let's say 40 or something, or 20, you could consider creating testlets. And testlets are just sums of 3 to 5 items, let's say. And once again, though, you have to know that they measure the same thing to sum them up. But once you sum them up, then you can use them as indicators in a factor analysis model, but continuous indicators. So they're little sums, so they're continuous. And then you can also use factor scores. And you can estimate those, as Bengt mentioned earlier. In general, if you decide you're going to use categorical methodology, you're going to, in general, need a larger sample than you do for the same model with continuous outcomes. And once again, if you really want to know how large of a sample you need, you could study that through a Monte Carlo study. And one important thing that we sometimes showed a 0 cell when we were saying the maximum correlation was 0.5, and 0 cells should not be in any of the bivariate tables between the items. So if you have 2 binary items, it's going to have a 4-celled binary table. And a 0 cell there is not really acceptable. You need to have something other than 0 in that cell, preferably several observations or several frequencies in that cell. So the methodology was not developed for bivariate tables with 0 cells. This implies a correlation of 1, and how to actually deal with it has not been, no way that everybody agrees on has been settled on. So if in Mplus you have 0 cells, we're going to tell you that. And then you need to consider whether you're going to keep both variables in the model. It may be that your model just simply isn't large enough. You know, you need a larger sample to get cells that aren't 0. So that's something that we now give people warnings about. And then we have further readings, which, Bengt, you might want to say something about before we take questions, which I think we should do at this point.
So there's a lot of good writing on this topic. And here's a classic paper, Full Information Item Factor Analysis by Bach and others. That actually compared ML to weighted least squares. Back in the days of, well, actually, no, this one is an article on full information maximum likelihood. Let's see. I'm thinking about another article.
There is no more.
Oh, okay.
I checked.
Yeah, so there's an article by Bob Gibbons and others that compare ML and weighted least squares and find that they're very similar. So you don't lose that much information by using the limited information weighted least squares estimator. I think you have that reference at the end of your handout. Flora and Curran did a psych methods applied article. They tried to figure out if these approaches were sensitive to the underlying normality assumptions, particularly looking at it from a weighted least squares perspective with you know, working with the tetachoric and polychoric correlations, which assume U star normality, which we have put an equality with the normal factor, normal error situation. That's a worthwhile article. It shows that you have quite a lot of robustness to deviations from normality in terms of this approach. In this building, there was a time when George Bornstedt and Bill Eaton got together and produced a volume of sociological methods and research on the ECA. Who knows what the ECA is? You're in the house of ECA, yeah. Epidemiological catchment area had several sites. One of them was Baltimore, I believe, yeah. So anyway, they put together a volume on analysis of dichotomous symptom data and dichotomous criterion data, and different authors to use different analysis techniques I did this dichotomous factor analysis. Others used latent class analysis. And some others still used grade of membership modeling. So that's a worthwhile thing to read. Together with my former student David Kaplan, we did a paper in British Journal of Mathematical and Statistical Psychology, which might be useful. Has to do with comparing categorical variable and continuous variable techniques on factor analysis of non-normal Likert variables, looking at some of these correlational attenuation matters that Linda talks about. So, you know, the problem is twofold. You get attenuated correlations, but the correlations are attenuated differently depending on the marginal distributions, on the univariate distributions. And no association coefficient should be dependent on the marginal. So given that you get different degrees of attenuation, even if you start with a one-factor model for the U stars, but have U's that have different univariate distributions, you're going to get a whole range of different U correlations. So that treating the variable as continuous, you might conclude that you have two factors, whereas in reality you only had one factor for the U stars. So anyway, that being said, then we should take questions so you get your break.
All right, we have a question here.
I have a couple of questions. First of all, I tried to perform an IRT model, and I took the translations, including the lambda, the thresholds to the identical discrimination framework. Is there
The only thing, okay, so the question is, or the statement is this gentleman did an IRT model and he did not get the translation. There's a couple of reasons for this. If you had a covariate, you wouldn't have gotten it. If you only had a one-factor model, categorical outcomes, no covariate, and you didn't get it and you're using a fairly recent version, then you should send that to support because you should get it. And it does come out. Had it up here. So then there's probably something else going on. And I would be happy to look at it and tell you.
And again, we want to emphasize you don't have to make that conversion just because you do dichotomous factor analysis. We believe that the Mplus metric is quite interpretable.
Other questions? Way in the very last row.
I have three very quick clarifications. One is if we have several categorical outcomes, am I to understand that it would be best if we make them look like they're on a Likert scale, so it would be best to try to make them looking normal. So if we have like from 0 to 5, if we can categorize them in a way that would create some sort of a normal distribution, then that would maximize, they will be attenuated, but that will minimize attenuated correlation, is that correct?
So I think the question has to do with what if you have a ordered polytomous variable, can you make it look more normal to minimize the correlation or attenuation? I guess you're going from a 7 categories to a 5 category, collapsing categories?
Right.
You can certainly do that. If you insist on staying in a continuous variable framework, you lose some information, of course.
Okay.
But you can certainly try to collapse categories and make correlation attenuation less. I don't know the trade-off between keeping the original information versus being able to squeeze it into the continuous framework.
For the CFA, if we have like the RMCA and all the other ones looking really good, but the CFI is not that good, show which of the fit indices are more important for the categorical outcomes, or they're all. So I get like really good RMCAs and WRSMRs and all that, but the CFI is not that good. So shall I take that to indicate that the model is not good?
So the question is about fit indices that come out. The usual SEM fit indices come out with the weighted least squares approach. And which one would you go by? That's very hard to say. The dissertation by Yu, which is on our website, suggests that overall in her simulation the CFI index was the most reliable. But it's really dependent on the data situation, I would think. Other fit indices might be good for in other cases. And like Linda suggested, I think you may want to look at fit indices from a couple of different families, or like was done in the Yu dissertation, actually do a simulation that's geared towards your data. So we did that for the Holtzing S1 Ford data, I believe, to judge which fit index would work best there. So I don't think we know enough in that area to say for sure for all situations.
Way in the back over here.
First, just a reminder, I mentioned to Bengt earlier, if you have time, if you could mention briefly today how to generate data, Monte Carlo data that are categorical. If you have time. If not, I'll go through it before. My question is on slide 120 on the screen plot.
So could you read? Oh. Okay, go ahead.
What importance do you attach to the dramatic difference in the magnitude and the eigenvalues, the big steep drop there, if any?
Okay, let's start with the second question first then, on slide 120. Steep drop here, the first eigenvalue is very big, which would then, if you do a principal component analysis at least, would indicate that one component explains most of the variation in the data. And to the extent that that can be translated to factor analysis, it would say that one factor would explain a lot of the correlations among the items. So the other factors that are needed are minor relative to the first one in terms of explaining. Probably the best way to say that the minor factors, 2, 3, 4, or 2 and 3, would explain a rather little variation in the items. The first question, that was a question about how to do Monte Carlo simulated data that are categorical. And that's quite easy. It's described in Chapter 11 in the user's guide. You just generate categorical data. So this is a generate option where you specify what variable type you want to generate. So you can generate categorical, continuous, combinations of the two, counts, etc.
And okay, I was just saying also if you're interested in a factor analysis model,
CFA.
SEM model. So
CFA.
I can't hear.
CFA model.
CFA. Okay. So if you go to a CFA or to Chapter 5, you find a CFA model with categorical outcomes, which I don't know the number by heart, but it's one of the early ones. Then you get the Monte Carlo counterpart for that, which which should be on your computer or it's on the Mplus CD, and then you start from there. That'll show you how to use the generate option, and it'll be a good starting point for you. Okay.
And you can generate under probe it or load it, depending.
And that's explained in the user's guide under the generate option.
Lady in red. Sounds like a movie title.
You mentioned the estimators of weighted least square and the maximum likelihood estimator, but what about the unweighted least square in this situation?
So the question is about the ULS estimator. Do we have a ULS estimator in addition to the WLS and ML estimators for categorical outcomes?
Yes.
And the answer is yes, apparently.
But is there any reason why you didn't mention it here? Is that because you don't believe in it so much? Or?
No, for exploratory factor analysis, I think it's fine. ULS is fine for exploratory factor analysis. ULS can be a little iffy when you go beyond that, because it says that all the sample statistics that you work with have the same variance. It has weight matrix that has the same weights 1 for all of the sample statistics. So for instance, if you have a model with mean structure, thresholds, and correlations, they don't have the same variances. ULS wouldn't necessarily be a good estimator. But for exploratory factor analysis purposes, it's just fine, I would say. Yeah.
And how about, given that you have a model where you first estimate some correlations, how do you take that into account when you estimate the standard errors when you apply, for instance, the maximum likelihood estimator to the CFA? Do you take that? Yeah. Do you take that into account? Do you understand?
Yeah. So the weighted least squares estimator.
Say the question.
The question was, how do you take into account that the variables are categorical if you're fitting the model to a correlation matrix? I think that's what you asked. No?
No, I think I'm asking that first you estimate the tetrachoric and polychoric correlations. So these are estimates, and then you use them for instance, for a factor analysis.
Right.
It means that, and when you then calculate the standard errors for the factor analysis, how do you take into account that you base it on estimates? Normally you have to what do you say, adjust the standard errors for the last step. But I don't know if you do.
Yeah, no, that's the line of thought I was going after. You estimate the tetrachoric correlations, yes, but you also estimate a so-called weight matrix. This is the weighted least squares estimator, which is the asymptotic covariance matrix for those tetrachoric correlations. And that weight matrix is used to compute the standard errors, taking into account that those tetrachoric correlations come from these bivariate categorical tables. So in both the standard error and chi-square estimation, you take into account that the raw data is categorical. So the input for the program, if you want standard errors in chi-square, cannot be just the correlations, but the raw data. And that's the typical input we expect for weighted least squares with categorical outcomes.
Down here?
Someone had asked a question, I think when we were around page or slide 127, 128, with respect to complex survey data, and you had said the solution was to say type equals complex. And I'm wondering, you also have type equals 2 level as an option. What distinguishes when you would want to use one versus the other?
Okay, so the question is when you would use type equals complex and when you would use type equals 2 level to take into account that you don't have a simple random sample. And this is discussed in the beginning of chapter 9, but basically what it says is that you use complex when all you want to do is correct the standard errors and the chi-squares for the non-independence of observations and weights and whatever. But type equals 2 level allows you to also model data on both the individual and the cluster level. So that would be the short answer to that, while taking into account non-independence of observations.
The somewhat longer answer is that in factor analysis, it's probably safer to use type, although more difficult, more involved, to use type equals 2 level. If the common occurrence, if the situation is what it usually is, namely that you don't have the same number of factors on the 2 levels. It has to do with a model being aggregatable or not. Aggregatable or not. Type equals 2 level is safer. You probably don't go much astray with type equals complex. And that's a little bit different. That's a different difficulty wrinkle than what you see in standard linear or logistic regression, where you don't have that issue.
Over here?
Yeah, as a follow-up, can you do exploratory factor analysis at level 2 and confirmatory?
Oh, go ahead.
Question is, can you do exploratory factor analysis in multi-level situations, 2-level situations? And yes, we'll show you a lot of exciting example of that in March 2009. But as a preview, in version 5 of Mplus, we have a very exciting new development, a weighted least squares, a 2-level weighted least squares approach, where you can do exploratory factor analysis on both levels with rotations, rotating simultaneously. And you can even have an unrestricted model on one level and a factor model on the other, and vice versa, to really test your way through that. And we presented, that's work led by Timur Asparoho at Mplus, and we have a paper that we will shortly finish up and post on our website where you can read about those techniques. But that's described in the version 5 user's guide and under the features that were added for version 5.
Okay, another question?
I had a question about IRT with the covariates. You had mentioned that you don't get the difficulties and the discrimination when you include covariates. How do you specify it within the model, and is there any way that you can actually get those values, either calculating them on your own, or would you suggest stratifying if you had enough data, say if you want to look at gender differences?
Okay, so the question is, if you have an IRT model with covariates, how do you specify it has covariates? And then can you have the translation to the IRT metric? And you would just do what we saw yesterday. You would do F on X. So you use the on to include a covariate in the model. And then usually IRT doesn't have covariates, so then does the translation hold? I don't know.
Yeah, you can create your own translation in that case by using the model constraint feature, where you define new parameters where, you know, like we showed yesterday for a standardized and reliability coefficient, and thereby you get the point estimates and the standard errors for those point estimates.
Over here?
So then is there a way that you can save your IRT scores and then include them and then use them as your outcome variable in another kind of analysis?
So the question is, can you save the IRT scores, by which I think you mean the theta, the latent variable estimates for each person?
Yes.
Save them and use them as, say, a predictor variable for another model.
Okay, well, you can save factor scores. I guess my question to you, Bengt, would be, are those IRT scores or are they in a different metric?
Those would be IRT scores if you do the setting that we showed you, namely fix the factor variance at 1, and by default the factor mean is 0. So yeah, they would be IRT scores, and if you feel that they are sufficiently well estimated, close enough to the true scores, yes, you can use them as observed variable in another analysis.
And that would, you just say save equals F scores in the save data command.